Welcome back to the lecture series on bioenergy. So, let us catch up where we left in the last class. So, we talked about the pyrolysis technique, where we talked about slow pyrolysis, flash pyrolysis, and in the slow pyrolysis we talk about the carbonization process, which leads to the formation of solid fuels. Whereas, in the flash pyrolysis we have talked about the liquid fuels, what we get in the form of bio-oils, and the transformation of bio-oils using zeolites and hydrogenation processes. And the third, where we do a flash pyrolysis to form gaseous fuel, which we have not gone into the gasification process. So, in the last class I told you that in terms of that solid fuel formation, depending on one highlighting feature which is emerging as we are walking through this whole process of pyrolysis, which pretty much is the reason why we have so many carbon based fuel which has formed underneath the earth because of high pressure and high temperature over centuries, the formation of coal, formation of even diamond, formation of graphitic carbon, formation of petrol, formation of natural gas. So, if you consider this whole earth as a reactor vessel, some in the surface, some inside the ground, deep inside the ground, things get buried. So, pyrolysis has been happening in a reaction in the absence of oxygen has been happening since the very beginning. Okay. So, based on the level of pyrolysis, based on the route of pyrolysis, based on the conditions of pyrolysis, the product changes. So, that is the thematic, that is the most beautiful emerging thing what we are observing. As you must have seen, when we process the same stuff using zeolites, it has a different fate. When you do hydrogenation, it has a different fate. So, when you do a flash pyrolysis, we could get we could get liquid as well as gaseous fuel, whereas with a slow carbonization what we get are just solid fuels. Okay. So, just coming back to the slide, if you remember, this is the slide where I ended in the last class. So, you have the biomass. Depending on the biomass, what are we talking about? You can pyrolyze it in the absence of oxygen and at a temperature of 500 degrees centigrade. Okay. What you get is solid charcoal, which is the carbonization process as I was highlighting, liquid and fuel gas. So, today what we will do, we will talk about a very specific kind of biomass which leads to carbonization, leading to the formation of graphene like molecules or a very special kind of graphenes which is the need of the hour. So, what is the philosophy behind this? So, you have a wide area of biomass on the floor of earth, okay, this biomass. So, use different kind of conversion technologies, of biomass conversion technology to convert it into fuel. Okay. You are using these fuels to generate electricity. Okay. Just the same way you use, if I parallelly look at it, you are using natural fuels like coal and other things to generate electricity. Okay. Now, this electricity has to be stored somewhere in the form of charge storage devices or storing in charge storage devices. Charge storage devices. Now, most of these charge storage devices are either lithium, cadmium batteries, lithium sulphide, lithium cell batteries likewise, Now think of it, this is the philosophical side. If these charge storage devices are also obtained from the biomass, how the story will be. So, essentially our life will revolve around biomass technology, and the root is the same. As I told you, the thematic is the same, the conversion technology. What is the conversion technology you are using? So, today we will talk about a conversion technology of biomass where you can directly convert biomass into graphene like material, which is way more efficient than normal graphene. And in one of the classes in the later half, we will have a video demonstration of how such graphenes could, which is derived from the biomass sources, could be made into a very good functional supercapacitor. So, we will have a video demonstration of this process in a later class in the advanced technology. So, this is part of one such advanced technology where, following the thematic that what kind of process conversion technology is being used, you can transform the biomass to different kind of materials. So, here the conversion technology what we will be following is pyrolysis. Okay. And the material, the biomass, is a natural fiber. One of the very prominent natural fiber which is used for clothing is silk. So, this is one example where silk, which is derived from silk cocoon, all of you have seen silk at some point or other, either in the form of clothing or bed sheets or any kind of textiles or some military gadgets what have been used. So, silk is there for a long period of time. If those of you are not aware of silk, it is fairly simple. It is synthesized or it is made by certain group of insect or a huge group of insects. So, just clear your concept, there are arthropods or the family of insects which chew a lot of vegetative materials, and from their mouth they give out a saliva like material, and that material is rich in protein, and that is what is called as silk. Okay? So, there are some 15-20,000 such species of insect which gives out that exudate from their mouth, and that exudate is very rich in protein and other biomolecules, and they form, sometimes they form a complete coating around that insect in order to allow it to go through second couple of stages of their life cycle, their dormant phase, which leads to the metamorphosis where simple larvae gets converted into a pupae, which is the dormant phase, to a butterfly. Sometimes they form very nice thread like structure or called spider net. You all of you have seen this. This is a common, those who have seen Spider-Man movies, they all are aware of the spider net like this, which is also nothing but a form of silk. There are some technical differences between the different kind of silks, whereas all of you have seen silk cocoons from where the silk threads are being taken out. So, this is silk cocoon, this is spider net, they are all different form of silk. The only basic difference between these two silk is, if you see this thread is something like this. If you see a cross section of this thread, it will look like this. So, as if a tube inside another tube. So, the inside red tube is called fibroin, and the outside blue part what you see is called sericin. this is what regular silk what we use in our clothing consists of. So, what they do, this sericin it is a protein and fibroin is another protein. So, this protein is very gummy in nature, it sticks. So, different fibroin threads stick to one another using this sericin protein, that is why it forms a structure like silk cocoon. It is a very compact structure, whereas in the spider net what happens, these threads are fibroin, same fibroin with of course different sequence of the proteins, it is a protein, but the spider net lacks this particular component, the sericin part. So, this is minus sericin, and that is why you see the spider net to be spread out. So, they do not adhere to one another, thread does not adhere to one another. In order for the thread to adhere to one another, they have to have a gummy like material. So, then they form a cocoon like structure like this, whereas a spider net is more like a spread out, because that gummy protein is not there, but they all are silk, and there are at least 10,000 to 15,000 or maybe more species of silk threads available, but very handful of them has been over the years have been cultivated or are being used for agro purposes. So, one of the famous one is, which is across the world which is used, is called Bombyx mori, which is Bombyx mori, it is a white color silk cocoon. The other wild species, so this is the domesticated species silk cocoon. There is a wild species which is called, which is very common in India, which is called the Tassar silk cocoon, Antheria myelata, which is a scientific name. There are other cocoons in India which are found in Assam. So, today what we will be talking about, this one of these wild cocoons which is Tassar, which is wild, and it is found, it is widely found in several parts of India including Madhya Pradesh, Chhattisgarh, part of UP, and several part of Bihar, especially Bhagalpur and all that region, then down south. So, but these are all wild silky. So, now looking at it, so this is a form of a biomass. So, now we are talking about a protein biomass, which is, so as of now we are talking about lignocellulosic carbohydrate biomass. So, here we are talking about protein biomass in the form of a silk cocoon. Okay. So, what happens? So, as I have already told you, so the insect passes through, most of these insect passes through 4-stage life cycle. So, you have a larvae, which is something like this, all of you have seen these larvae, you know. So, these larvae eat on leaves, lot of leaves, and they put on a lot of weight, and then this larvae from its mouth gives out this protein rich fluid, by which it forms a coat around its own body and it goes into a dormant phase. So, this is the dormant, this is called a pupae. Okay. And then after a certain day, that can vary from 20 days to 9 months depending on the species we are talking about, the insect, butterfly emerges out, leaving behind the open cocoon, and the life cycle goes on. Then this butterfly again lay eggs, and likewise the larva is formed. So, this structure is nothing but a protein biomass. Now, if you take this protein biomass, and so you have silk cocoon, and if you pyrolyze it in argon environment, AR or nitrogen environment, sorry, AR, argon or nitrogen environment, what you get is a very interesting kind of, so this is what is a native graphene looks like. It is a single layer carbon. Okay. So, all these are, so let me put it, carbon, 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 like. Now, this is what you, one second, let me just rub it off. So, this is what is a graphene looks like. Now, when you burn or pyrolyze it at a temperature of around 400 degrees centigrade minus oxygen, again the same carbonization process we are talking about, what you get is very interesting. This is your native graphene molecule. Just for your comparison, I am redrawing it with all the carbons attached. Okay. Now, whereas this situation what you are getting is something slightly different from such a uniform structure. Get something like this. Okay. So, you have some of this nitrogen instead of carbon coming in, and I will tell you from where they are arriving. And okay. And you have certain nitrogen here, certain nitrogen here. So, what do you see? So, if you compare these two structures, so here you had nothing but carbon, 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 carbon. Likewise, here you see as if that matrix is now being doped with nitrogen, from where the nitrogen is coming. So, think of the structure of a protein. We will come back to this structure again in a second. Okay? Think of the structure of the protein. So, this protein what we are talking about is essentially, if you see a protein chain, this is a protein chain. Okay? It is a polypeptide. Okay? So, the polypeptide is made up of amino acids. So, you have these amino acids, AA stand for amino acids, different kind of, there are 21 different kinds of amino acids and they are attached to each other. Okay. Now, they are attached to each other by a planar bond structure, which is peptide bond. Okay. It is this bonding which is all over the place. So, they are, all these amino acids are bound to each other, and what you see, the protein molecules have bunch of nitrogen in it. Now, once you take this stuff and pyrolyzed it, what is happening after pyrolysis? Pyrolysis leads to something similar to this, where this whole structure, this linear chain of protein, which was something like this, gets transformed into, it compresses itself into a geometry where the carbons feel much more at ease with each other, because you are, because I told you that there is a structural rearrangement which is happening, and since you are not providing any oxygen, so there is no carbon dioxide going through. Whatever is there and whatever little oxygen may escape, it will escape through, but whatever molecules are there, they are already present there. And if you think of it very carefully. So, you see carbon, when you talk about carbon, it has atomic number of 6, and we talked about nitrogen, it has atomic number of 7. So, you have one extra electron which is present here. So, the molecule of graphene as such needs some kind of a dopant, and introducing a dopant by an artificial technique in terms of say nitrogen, which has one additional electron, in order to increase, say for example, I want to increase the charge density of this molecule, okay, charge density of this molecule, just rho I am showing for the density, charge density of this molecule. So, in order to increase the charge density, I have to increase the number of electrons, but carbon I cannot do anything. So, I have to introduce something which is little more than carbon. So, my nearest neighbor to carbon is the nitrogen, but how to introduce the nitrogen? I have to do a lot of thermal processes and everything, but instead if we follow the age old technique what nature has done, by a simple pyrolysis, what will happen, these within the protein molecules where there is so much nitrogen present there, those nitrogen will rearrange into a very interesting conformation, and the possible conformation in the next, let me draw the next picture which will give you an idea about what are the possible conformation it can go. You will realize, so these are the possible conformation it can attain. Okay. So, this is a simple standard graphene network which I am drawing, and then I will introduce all the different dopant which are getting into the system. Okay. Okay. So, out here now I am introducing all the dopants with different colors. Okay. O minus, okay, where I have a small positive charge. This is one such moiety which will you observe. Then you will observe something more interesting. You will have say nitrogen here, nitrogen plus, which is that. Then you have another nitrogen out here, and I am just circling this. I will tell you why I am circling this. Okay. Then you will see some of the, one second, let me just redo it, something like this. You come across nitrogen and hydrogen, another form, then you have nitrogen here. So, they have different names. So, this is called pyridinic oxide, this is called quaternary nitrogen, this is called pyrrolic nitrogen, and this is called pyridinic nitrogen. So, if you observe in a simple structure of graphene following a very low energy technique, you just expose them to 400 degree centigrade and you get to one of the very high quality nitrogen doped graphene. So, what is this? This is essentially what you are getting is nitrogen doped graphene. As a matter of fact, making these kind of nitrogen doped graphene was done in India for the first time. So, you can refer to the following paper which will help you to kind of know a little bit more about it. In volume 160, April 1st, 2015, it was published in Electrochemical Acta. Okay. Please go through it, that will kind of give you an idea. 253, the journal is Electrochemica Acta. This is the reference where you will see heavily, so the paper title is heavily nitrogen doped graphene supercapacitor, and this is what we will be demonstrating in the class. Supercapacitor from silk cocoon. Okay. So, by a very simple technique, what we are telling, using a simple silk cocoon, and there are processes which are following condensation, carbonization, which is basically the pyrolysis, 400 degrees centigrade in argon or nitrogen environment. What you are getting is approximately 15% doping of nitrogen. This is in itself is a big record. To getting a 15% nitrogen, in other words, out of 100 carbon molecule, you could insert at least 15 nitrogen doped molecule. So, just try to imagine. So, you have 15 nitrogen means you have 15 extra charge moiety is what you are adding, which essentially was not possible with a pure carbon network. So, the charge density and charge storage potential goes up at least 15 units more as compared to the native graphene. So, having said this, I will highlight some very interesting aspect of it, which will kind of help you to again appreciate that how the pyrolysis can make difference. So, we talked about that this was done at 400 degrees centigrade, where one gets 15% nitrogen doping, okay, nitrogen doping in graphene, which we call as nitrogen doped graphene. Okay. Now, say for example, you raise the temperature to say 800 degrees centigrade of pyrolysis, you will be surprised the nitrogen percent goes down to 3.4 to 5.1. This is the kind of fall, and if you go, and there are reports which, yeah, I think this will kind of give you an idea about minus oxygen, just showing pyrolysis in the presence of argon or nitrogen. Okay. So, this will kind of give you an idea that how temperature plays such a critical role and the conditions plays such a critical role in pyrolysis, that you can change the complete physical properties. Its whole electrical property changes if you increase it 400 to 800. So, these are some of the very interesting technologies which are evolving, that biomass is not only for fuel, it is could be used for energy storage material, and one of the very high profile energy storage material. And these are the discoveries which are done in India for the first time. It was shown that you can use this kind of thing, and you really can achieve something which we as Indian are the first one to show that it is possible. So, these are the new dimension and newer technologies which are coming up, highlighting the fact that biomass could be converted into versatile product, and someday the whole area of bioenergy will open up to these newer and newer discoveries, which will make it a much more compact science, like biomass engineering science, where biomass converting into fuels, biomass converting into energy storage devices, biomass directly making batteries, which will be talking at some point. So, if you look at it, the integrating features or one common thread is that what kind of conversion strategies are we following, and how that could influence the fate of that particular biomass and what kind of biomass we are picking up for the conversion process. So, I will close in here. So, next we will move on to gasification and other few advanced technologies. Thank you.